Okay, we'll probably start in about 30 seconds or so. So I guess today's live stream is probably the most important one. As you guys can see, is worth about almost half the whole paper. So we're just kind of, yeah. For anyone who's already joined, if you do not have, I guess, paper or a calculator with you, you might want to get one. Okay, I reckon about 30 seconds past, so let's just start. Okay, so first things first, we're going to start with circuit devices. Seems simple, but you get marks for that as well. So let's just look through this very quickly. You guys can either, I guess, you guys can either just comment down like what you reckon these are or write it down yourself, but I'll just go through them. So if you look at this column here, they all have the same, I guess, basic design. They all have a rectangle, and then you kind of build upon the rectangle. Now, the rectangle by itself is just known as a resistor. This is the thing which slows down everything moving in the circuit, which I'll explain when I go over circuit rules, like the fundamental things you need to know about circuit. So these are all types of resistors. So if they give you this, just link it. So you got a resistor here, definitely. I'll just write resistor again. But what kind of resistor? This is known as a variable resistor because it has an arrow going through it. Now, from English, I guess the word variable would mean what? Something which is changing, right? So you kind of signify change via the arrow there. That's how I remember it personally. This one here, you got a hockey stick. So this is known as a thermistor. It's to do with temperature. If you were to break this up in two words, it would be thermal resistor. Yeah, so thermal resistor, just AKA a thermistor, is a resistor that depends on temperature. This one here is also a resistor. But if you guys look at the arrows, because physicists cannot draw it, this pretty much is just light. So it's to do with light. So it's light dependent resistor, yeah? So it's a resistor that depends on light for its function. Simple as that. Looking at these ones here, this one's a bit dodgy. It looks like a resistor, it's not. It got a line going all the way through it. This is a fuse, which is a safety device, which we'll go through. These ones, I don't know if I have to even go through these, but anyway, the ammeter and voltmeter, sure you guys have been using them in all the practicals you've been doing. M is a motor. By the way, have you guys been exposed to all the seven different electricity practicals in class? Did your teacher show you all the different practicals? Did they let you guys actually do it, or was it more or less just like a demo? Because it's kind of important for you guys to do the practicals yourself. So you got battery, you have a cell. Now, okay, just in case it wasn't explained in class, a battery, if you get any battery in the world and you actually rip it apart, you kind of find some circular silver discs inside it. These individual discs are known as cells. So several cells put together make up a battery, right? So cells are always just the one unit, and then more than one makes the battery. This one here is a diode. I might as well just give you a subliminal hint. Well, it's not really subliminal anymore, but they will ask you one of these in your test as a one marker. So you guys can guess which one. So this is a diode. This is a light emitting diode. Whenever you have arrows sticking out or coming into something, it's to do with light emitting diode. And that's it. These are all the devices you guys have to know for your exams. One of them will turn up. That's the easy one marked. Okay, now this is like the core of electricity, Ohm's law. And there have been cases where they give you the 15 marks just on this one topic, right? So what we'll do is we'll just kind of go through the basics. Now, Ohm's law, this is the formula for Ohm's law. You've probably seen it quite a few times. So voltage is equal to current times resistance. You might want to write it down. Another word they use for voltage is potential difference. So whenever you see potential difference, just automatically know that it's the same as voltage there. Yeah, they're both the exact same thing. Now, what Ohm's law kind of states is, rather than just memorizing the equation, Ohm's law states that when you have a fixed temperature, so when your temperature is the same, yeah, so let's imagine temperature doesn't change. They're saying that your voltage and your current, so I is current, and V's voltage, that your voltage and current are basically both directly proportional. Now, I think in maths you guys have covered like direct and inverse proportionality, right? But just in case you haven't, if two things are directly proportional, it just means that if one doubles, the other one doubles as well. If one triples, the other one triples. And the way to kind of plot this on a graph is very simple, just a diagonal line. So from this graph here, this graph is basically signifying or showing Ohm's law because it's stating that your voltage and your current are both directly proportional because you have a diagonal line. Simple as that. Yeah. So whenever they give you a graph like this, they say what they might ask you, what does it show? You can say it shows that your voltage or your potential difference in your current are directly proportional because the gradient is constant. So we're using quite a bit of math terms now, but that's what physics is about anyway. So your gradient is constant. That just means that you have a diagonal line. Yeah. Okay, so that's you have to memorize this formula, by the way. You'll be surprised how many marks you get just for using it. So yeah, make sure you memorize this formula. Now, Ohm's law applies to obviously this resistor here. And if you were to maybe get a 15 marker in this, what they'll do is they could obviously give you a mathematical question, like maybe 4 or 5 marks in this. Then they'll give you stuff to do with the actual circuit. Now, what you guys should have done in class, and I hope you guys have done it, but in class you were meant to design the circuit that shows Ohm's law. So let me just go through this. This is obviously a battery with your power source. This is your ammeter. This is your voltmeter. This is a fixed resistor, as we said. What kind of resistor is this? This one is your variable resistor. Yeah. Okay, so that's your circuit setup. So let me explain what's going on. Your end objective for this experiment is to plot this graph here. So this is the graph you want to get. What two values do you need? You need values for your current and you need values for your voltage, right? So what we'll do is we'll make like just a table, voltage and current, and you need to fill it obviously with numbers. Now, when you set this circuit up in the in the class, you basically there's two things you need to know. You definitely need to know where your ammeter and voltmeter lie, because it's very important. If I was to redraw this like this, I want you guys to tell me what's wrong with this circuit here. So I'm just drawing this with a slight modification. Because this comes up every single year. It's a bit weird. Why do you guys reckon this circuit is wrong? If you think about it, I'm hoping the right answer is that you guys picked out that this is in the wrong position, that's in the wrong position, right? But it's not good enough just to know that. It's better just to understand the reason why. So the reason why is a voltmeter acts like an infinite roadblock. So what I mean by that is if you put a voltmeter smack bang there in the circuit, we know that electricity is flowing this way, right? So you have your electricity flowing like this around the circuit over and over and over again. When it gets to the voltmeter, will it be able to pass through here if this acts as an infinite roadblock? No, this will literally block everything, so the whole circuit will not work. That's why you always put a voltmeter in parallel. That's the key word here. You always put the voltmeter in parallel with other devices so that it doesn't interrupt the flow of the circuit. So the way electricity will work now is it'll go like this. Ammeters are the opposite. Ammeters have no resistance. So ammeters have no resistance whatsoever, which means they do not affect the circuit whatsoever. So you just have your electricity flowing through there like this. When it gets to this junction here, obviously you can imagine electrons as humans. If you were had the option to go through there or to go through an infinite roadblock, obviously biologically you'll just go through there, right? Because there you're not getting past there no matter what. So everything will just continue in the circuit as normal. This is just on the sidelines, yeah? So please remember in the exam, voltmeter is always in parallel and an ammeter is always in series. Series just means that it's within the main circuit. Parallel just means it's within its own other branch, if that makes sense. So that's that. Okay, now going back to this practical here, you set this up to get different values for your voltage and your current. All you need to mention is that because obviously this is called a variable resistor, implies you can what? Change its resistance, right? So all you mention is what? Change the resistance of the variable resistor. And every time you change the resistance of this, it will affect this value and that value. So you change all you mention in the exams, you change the resistance of this, multiple values for your voltage and your current. You plot a graph and you should get a graph like that. Easy marks for that. Like it's dead easy. So yeah, that's quite important. Yeah, so don't worry about copying down everything. I'll probably take a picture of these and then send it to whoever wants it. So there you guys go. That's Ohm's law for you. Just remember the main thing, this law only applies when your temperature is constant. Yeah, so because they're phrased in different ways. They might say, what's the relationship between voltage and current when the temperature is constant? You just mentioned they're both directly proportional. Okay, moving on. This is where you get the most marks in your exam. I don't know if your teachers told you that you're meant to memorize all these 6 equations, but if you haven't started, you guys still go roughly over a week, I think, for your exams for physics. So what I suggest is every single day, just write all of these down over and over and over again until you memorize them. The ones that usually come up, like this is obviously the main one. Then you have this and this. For anyone who attended last live stream, we've already done energy, power, and time. So you guys might be familiar with this already. So these are like the main ones. Focus on these ones, and then obviously try those in if you have extra time. So what we'll do is let me give you guys about 30 seconds just to write this down. Let's see how fast you guys can write. Because we need to answer these questions based on those. And I don't want to keep having to like move like that, otherwise you guys will get a seizure. While you guys are writing this down, let me just explain. So V is the easiest one, is just voltage. Oh, done. Never mind. It's already there. The key things you want to watch out for is in physics, using any one of these equations would generally just be 3 marks. They're quite generous. But if it's 4 or 5 marks, what they do is instead of giving you just a normal number, they put like kilo before the volts or like kilo before the resistance or something. So you just need to watch out for these prefixes. Okay. Tell me if you haven't written down everything, but I'm moving on. So once again, I said this last time, when you tackle these questions, make sure you underline everything. Otherwise, you'll have a hard time of knowing what you're doing. So you have your power, which is what, 2 kilowatts, and you have your current, which is I. So I is current, just in case anyone joined late. And your I is what, 0.5 amps, right? And they want your potential difference. Remember, potential difference is just a fancy term for voltage. Pi and V. The equation we're going to use is the third one, right? Because P, V, and I. So you write the equation as you know it, as you'll usually write it. And then now we just rearrange it. We're trying to look for V. For anyone who hates maths or struggles with rearranging in maths, once you have this format, to make it into the triangle, which some of you might want, the thing which is on one side by itself always goes on the top, and then everything else goes on the bottom. Is that simple, yeah? So P was by itself, you put on the top, these two on the bottom. Now we're looking for voltage, so you put your finger over V, so it'll be what? P divided by I. So it'll be power divided by current. Our power is 2,000, almost fell for it. It's kilo, so remember to times it by 1,000. In electricity, you never want any kilo or micro or anything. So you end up with 2,000 over 0.5, and I think you get like 4,000 volts. Easy 4 marks, yeah? Sorry, 3 marks, I lied. All right, let's do the next one. So once again, guys, just try this yourself if you want. So you have V for voltage, which is what? 50. You have resistance, which is is it 5,000? Yeah. Ohms, and then you're looking for the current. Now, most of you probably already know which equation we're going to use, Ohm's law, which is the first and main one. So V equals I times R. Triangle is what? You put the one by itself on one side, you end up with that, easy. And then now what we're going to do is to find your I, it'll just be V divided by R. So you have 50 over 5,000, and then you end up with like 0.01 amps, I think. So that's a decent 4 marks. All right, gulp. This is about 6 marks here. Now you're probably looking at SHC and you're thinking, how is this related to electricity? It's not. I done it last live stream, but there's a reason why I'm doing this question over and over. You guys can take hints. So if you look here, write down everything you have. So you got power, you have time, you have mass, and you have SHC, right? In the exam, they do give you the formula for SHC, so let me just write it down. So you guys are quite lucky with that. SHC times change in temperature. You have to kind of fuse this with electricity. So we have this. What do they want us? So let's write everything we have. Our power is 5 kilowatts, but I might as well just now change it to watts, so 5,000. The time is 3 minutes, but if you guys remember last time, we said you cannot use minutes, you have to use seconds. So you times by 60, because it's 60 seconds in a minute. So we got power and time. We got mass, which is M, 2 kg. And you got SHC, which is all the way there, 4,200. And we're looking for the change in temperature. Okay, now let's look at this formula here and make it into a triangle first. Because I think last time I didn't tell you guys how to make it into a triangle. So if we use the logic we just used earlier, energy is going to be at the top by itself, E. Everything else is going to be at the bottom. So M for mass. You can just write SHC if you want. And then change in temperature. Triangle just means change. So that's the triangle. Okay, now to look for change in temperature, it'll basically be what energy on the top divided by the other two things, right? So you'll basically have, so your change in temperature will be energy over mass times SHC. We do have mass, we do have SHC. The only issue here is we do not have energy. So it's a double step question. You have to first look for your energy. If you look here, energy is power times time. So we might have to use this formula as well. You guys might have figured out already that you need to do power times time first to find your energy. Then the second step is you can use this formula. So to find energy would be 5,000 watts, which is your power, times 180 seconds. You end up with 900,000 joules. Yeah, so that's our energy. We just used the E equals P times T formula, which you have to memorize. Then now we just use this formula there. So your change in temperature will be your energy, which we found, which is 9,000, over your mass, which is 2. And then your SHC in the question is 4,200. And you just end up with your answer. So that's a nice 6 marks. Just remember, like, always write everything out like this and write all your equations out, because then you can kind of see what you have. You can tick them off, and you can just kind of circle what you do not have. And that means you have to use a different equation to find this, which we did on up there. Yeah, so once again, memorize these formulae. Always watch out for kilo or milli as well. Let me just show you guys quickly. If you have like milliamps, right? We know that we only want amps, or even millivolts. It doesn't matter what. As long as it's a small m, you need to get rid of the small m. So to get rid of the small m is the opposite of kilo. You need to divide by 1,000. Yeah, so if you had kilovolts, obviously you would times by 1,000 or kilo or whatever. But milli means you divide by 1,000. Just make note of that. All right, so that's that. Now comes the part of explaining how a circuit works, because to be fair, guys, you can memorize all the equations you want, but if you don't really get how a circuit works, you're going to lose like at least half of the electricity mark. So starting from the basics, we need to understand what battery does like properly, and we need to understand how a circuit works. So I'll give you guys an analogy in a second. This is your battery. Your teacher should have told you in a circuit you have electrons, so which are stationary in the beginning. Yeah, so that's the first, you should know that in the beginning. So when the whole circuit is off, you have electrons inside the wire, because the wires are metal, and they're not moving. What's the thing that actually moves the electrons? The thing that gives the electrons a good kick is the battery. So if I was to assign roles to all of these different terms here, these are the 3 main terms in electricity: voltage, current, resistance. Voltage is basically the thing that pushes electrons, right? So we agree that the battery provides the voltage, and that will push the electrons. When the electrons start to move, that's your current. Basically, your current is just the speed of electrons. And then resistance is basically obstacles in their path. So an analogy to this, if I draw this on the other page, it'll kind of look like this. So like you have like a massive boot or a shoe, and you have like a massive, like, this represents so this is like a shoe. The electrons are just like balls inside this tube. When the shoe kicks, or when the shoe actually kicks this electron, obviously going to be like a domino effect. They're all going to start moving. And obviously, the stronger the kick, the faster electrons move. That's common sense, right? So the analogy here is basically the kick or the force from the kick is your voltage. That's why if you use a 12-volt battery, you get more current than if you use a 6-volt battery, because this is like a massive boot and this is like a small boot basically, right? This voltage is more, so it provides a greater kick, so that means the electrons will move faster. Yeah, so that's how it works. The current depends on the voltage, because obviously if the voltage is more, your current is more because the speed will be greater. Resistance is basically, you can imagine like speed bumps, right? So if I have a road here, imagine your circuit is a road. Imagine you have like a speed bump there, another speed bump there. So you have quite a few speed bumps. These speed bumps here are representing resistors. So when electrons are moving because of that initial kick, you're moving them. When they get to the speed bumps, what's going to happen to their speed? Their speed is going to get less, right? Because obviously, as cars on the road slow down for speed bumps, same with electrons. So you can just replace the electrons with actual resistors. That's literally what's happening. So resistors slow down the current because they're obstacles. So that's definitely a concept you need to know. So you might want to write this. But the thing is, if voltage increases, current increases, right? That's the first thing we came up with today. Because obviously the voltage, the kick, if that is greater, your speed is greater as well. So let me just write here. Just so these are keywords to just make you relate to a kick, and this is like speed of. Okay, now what do you guys reckon would happen if resistance increases, so if now there's more speed bumps, what happens to the current? Or what happens to the speed of the electrons? We know that if there's more speed bumps, more obstacles, the current is less. Believe it or not, they give you 2 markers just for these kind of questions. I don't know why, but it's worth knowing. So because in the GCSE combined science specification from AQA, they mentioned that they test you on laws within a circuit. So that means this will definitely come up in your exam. So if resistance increases, current is less. But I just want you guys to think about it from like a real world perspective. Yeah, so that's how I think about it. Okay, so I hope that makes sense. Now, if we kind of if you look at something a bit more advanced, let's say that you have say you have a kettle, and obviously inside the kettle you have a circuit inside it, right? Say you have a circuit and it's powered by your mains electricity. So you get voltage from there and it powers this. Now they might ask you, for example, why does a circuit heat up when it's turned on, right? So why is it heats up when it's on? Now the way you think about this is when you turn something on, that means the battery's engaged and is actually pushing stuff across, right? When you push this across, these are moving very, very fast. Each one of these electrons carries energy, so that's very important. So every single electron carries energy. It's like pass the baton, kind of. So each one of these carries energy, and they're going to transfer energy across the circuit. Some of the energy will be wasted on heating up the walls of the circuit, aka here and there. So if some of this energy transferred to the walls, the temperature goes up. Yeah, so all we mentioned is so when a kettle is on, there is current, aka flow of electrons, right? So we do have a flow of electrons. They transfer energy to circuit, heating it up. Easy 3 marks there. Like a lot of it is logical, but it's logical once you understand how this concept works. Then everything else makes sense. Yeah, so that's how it kind of works. Just remember, as a complete circuit, you will have current, and that current basically means that you'll have electrons moving, and each one of them will kind of transfer energy. So that's how it works. Okay, looking at more advanced stuff, series and parallel circuits. Whether you like it or not, it will show up in your exam. So let's look at it very quickly. The first thing we need to know about a parallel circuit is, if I have two light bulbs, one like this, and then one like that, this is a parallel circuit. Definition is it has more than one route for electrons to travel. Because if electrons are moving there, they can either go this way, or they can either go that way. So they have basically more than one path to travel. Yeah. So that's how it works in a parallel circuit. In a series circuit, we have only one direction for your electrons to travel. So all of the electrons will have to go through there. Like they only have one path to travel. All right. So they might ask you benefits and disadvantages. A benefit of a parallel circuit compared to a series circuit is, let's imagine this bulb stops working, right? So it's completely destroyed. It basically now means that there's a blockage here, right? So because this is destroyed, electrons will not be able to flow through it. So any device which is not working in a circuit kind of acts as a roadblock. So now, if electrons cannot flow through this, will this work anymore? This will also not work because you're not getting the electrons to deliver energy to that. If you look in parallel, say this one stops working, it's fine. All the electrons do is, instead of going this way, they'll all just go through there now. So it'll still keep working. So parallel circuits, basically, if one of the branches is not working, electrons will just go through all the other branches. So it continues as normal. This is why in your home, say this is your kitchen light, say this is your bathroom light. I'm hoping in all our homes, obviously, if your kitchen light stops working, the bathroom light obviously still works, right? They don't really depend on each other. Obviously, if you had a garbage electrician who kind of set it up in a series way, so let's imagine this was the kitchen and that was the bathroom. Obviously, if the kitchen stopped working, then the bathroom would also stop working. So in homes, we use parallel circuits because they're better, yeah? Okay, now that was the theory behind it. Now, practical-wise, so if they give you this, don't get too intimidated, but they might give you something like this. All right, so if you look here at this circuit, I want you guys to think, will this light bulb turn on, yes or no? That's the first question you need to ask yourself. I don't know if any of you guys can comment, but it would be good if you guys can, just so I have a rough idea if the people get this or not. But do you guys think the light bulb will turn on in this circuit? If you get it wrong, I just want to just get some feedback. Okay, never mind. So the thing is, yeah, perfect. Oh, so Lily, you said that it won't. Okay, so you said it wouldn't. Now, you're probably saying it wouldn't just because there's a gap in the circuit there, right? Because this is opened, you're probably thinking that it will not turn on. But if you remember from parallel circuits, we said that even if one of the branches in parallel doesn't work, they'll just go through the other branch. Yeah, so it doesn't really matter. So if you look here, this is not working, so we can ignore that bit. But that means electrons can just flow through here and go that way. It's just like roads in real life, right? So if I give you, let me just give you like a real, so let's talk about cars now, right? So let's say you have this. Let's imagine there is a roadblock there for whatever reason. So this is just a road. That's a road as well. Oh God, you guys are like really, really lagging behind. You guys are lagging super behind. You know, the best thing is if you guys refresh your page, then you hopefully should catch up to where I am. But the way it works is you have the road right now. There's a roadblock there, which kind of represents this bit there. This bit just represents the normal resistor there, right? With maybe like 1 or 2 speed bumps. So what's going to happen? If you're a car, and you're a driver, hopefully you're not dumb enough to go there and just stop there for the rest of your life, right? What you're going to do is you're basically going to go through there and just continue with their journey. So that's what we're kind of saying here. Electrons, they have some intelligence. So they know that this is blocked off, so they're not going to go through there. They'll also all go through there instead, and they continue their journey. Yeah, so it's very important. If you have a parallel combination, as long as one of them is complete and not like a gap there, they'll just go through the one that's, complete with the rest of the circuit. That's how it works. So that means in this case, it will turn on. Yeah, so don't fall for it, guys. It will turn on. I'll show you a scenario where it might not have turned on. If everything was in series like this, and then you have the gap there, then you're 100% correct. This will not turn on because there's a gap there, and if you think about the electricity will get stopped there and you won't be able to jump there, yeah? So just please remember that in parallel, it'll just take the path which is actually working. Okay, that's fine. In terms of, wait, let me think. In terms of, trying to think if I missed anything out. Oh yeah, AC and DC, how could I forget? Whoops, that's from last time. Yeah, don't forget, guys, this is like the most important bit. AC and DC. Now, the thing is, just ending with AC and DC. The AC just stands for alternating current, and then DC stands for direct. So what I'll do is just quickly explain to you how it works. That's another requirement in the exam, so it might come up. So if you just have a normal circuit like so, we know that with direct current, it just implies that the electrons are only flowing one direction, right? So it'll only be going clockwise. So it'll keep going like this. They go to the battery, get pushed again or kicked again, and they keep moving on, kicked again, keep moving on, right? So this is basically direct current. And with direct current, we just say current flows only in one direction. So that's very important. Now with alternating, you draw the same circuit again. And then what you have here is you do have them going clockwise. They're going clockwise like so. Oh, this pen is terrible. But then what happens, once they reach the battery will now kick them the other way. So now they'll start moving anti-clockwise. And then when they get there, they'll go clockwise again. So basically, they're going clockwise, anti-clockwise, clockwise, anti-clockwise. So all we say is with alternating, direction of current keeps changing. Is that simple? Yeah, so that's the difference between AC and DC. Another like 2 or 3 marker question. They give you might be wondering why it's 2 marks. 1 mark is for mentioning that it's current. The other mark is for mentioning the direction, whether it's one direction or a change in direction. Yeah, so it's a nice concept, quite easy. Okay, I think with let's see, because for combined, so we went through that. We went through trying to think if there's anything else left. Oh yeah, there is one thing left. A very simple one. This is specifically to do with resistors in parallel, and then I promise we're done. So resistors in parallel, let me just give you the most basic example. Let's have 2. So this is first in series, and I'll do parallel. So let's imagine you got 100 ohms, 100 ohms. What's the total resistance here? Seems like a very simple question. The total resistance here would just be what? 200 ohms. Do you agree with that? Because we just added them up together. The reason why we add them up together is because, like I said, if you have an electron in the circuit, it needs to pass this one and also go through the next one. So it has to pass both of them, which is 200. Yeah. Now, if you look here, in parallel, they don't require you to do calculations in parallel. They just require you to understand the theory. So they won't ask you what the total resistance here is. But what they might ask you is, what do you reckon? What might it approximately be? So the total resistance in parallel is always this is just a rule. You don't worry about the maths behind it for now, because in combined they don't require you to know this. But if they give you this, just know that in the exam, this resistance would just end up being 50. The reason for it is just because if you have an electron, as we said, it only has to go through one of them. So you might think it just only has to be 100, but there's a reason why it's actually 50. Don't worry about it. Just memorize it for now. If you want to do it, if you're crazy enough to do A-level physics, then you can know it then. So electrons, they go through only one junction, which means that your resistance in parallel is always going to be half of just any specific one. Yeah. So if I give you another scenario of two resistors of 2 ohms and 2 ohms, the total resistance here will just be 1 because you just half any one of them. That's how it works. And if they ask you for a reason, all you mention is what? Current, or all you mention is basically current splits in a parallel circuit. Yeah, aka your electrons, some electrons will go there, some electrons will go there. But that's how it kind of works. Yeah, I mean, I think apart from Ohm's law, everything else more or less done for electricity. Yeah, so like I said, this is pretty much it. Just remember, guys, if you missed the live stream, just watch everything from the beginning, because I kind of went through everything you need for the exam, more or less. If you have any questions, feel free to email me, or you can find me, I guess, at school sometime. So yeah, all right, take care, folks.